Our first talk today is Challenger Mishra from Cambridge, and he's going to talk about neural network approximations for Calabi-Yau metrics. So, Challenger.
Thanks, Alexander. Thanks so much to the organizers for inviting me for this conference. It's a collection of fantastic people with similar interests, so thank you very much. I'm going to talk about our recent paper, which appeared at the end of December, on modeling Calabi-Yau metrics using neural networks. Before I begin, I would also like to state that I have recently joined a new machine learning group in Cambridge, hosted at the Department of Computer Science and Technology. And there's a bunch of machine learners as well as domain experts from other disciplines, theoretical physics, computational biology, material science, etc. So we are looking to work using machine learning to solving some of the important problems in our respective disciplines. Right. So this is the paper that I'll be talking about today. It's titled Neural Network Approximations for Calabi-Yau Metrics. Now, there's a bunch of related work to cite here before I even begin. There have been loads of approaches towards obtaining numerical Calabi-Yau metrics. And when I say numerical, I exclude machine learning efforts in this direction. So there are these quite a few different papers. Of course, the work due to Hedrick and Weisman on numerical Richie flat metrics on K3 is an important paper in this direction. And Donaldson's papers resulted in these algorithms that can numerically compute Calabi-Yau metrics. Now, we all know that recently there has been fantastic progress in obtaining analytic Calabi-Yau metrics due to Shamit Khachru and others. It's exciting times to be studying or researching metrics of Calabi-Yau manifolds. Right. Now, machine learning, the use of machine learning in looking at the metrics on Calabi-Yaus is fairly recent. In fact, Anthony Ashmore, Yang-Hui He, and Bert Overholt wrote this paper earlier, where they could predict higher order corrections to Calabi-Yau metrics from using the Donaldson's algorithm. There has been very recent work. So the rest of the three are more recent. There's work due to Michael Douglas and company, and also Lara Anderson, James Gray, Sven, Fabian Raghuram, Nikhil Raghuram, and others, some of whom are in the audience. Finally, Vishnu Jajala and Damian Mayorga Pena are my collaborators on this paper. So that's the first paper on this list. Right. But even before getting into the question of metrics over Calabi-Yau manifolds, I wanted to motivate Calabi-Yau manifolds from a string theory perspective. I come from the heterotic string side of things, so I would like to motivate it from that direction. So Calabi-Yau compactifications of heterotic string is, of course, one of the most promising avenues for string model building. And often an assumption is that the space-time for the effective field theory is a direct product between, let's say, a maximally symmetric space in 4 dimensions, which is aimed to approximate our, conventional 4-dimensional space-time, as well as an extra-dimensional part, which is 6-dimensional. Now, nothing further can be said about the extra-dimensional part at this point, unless you make certain assumptions. Of course, we are interested in a theory of gravity. So this extra-dimensional part, this X6, as I mentioned, has to be Riemannian. And we also require it to be irreducible, because having a reducible extra-dimensional part makes it difficult to reconcile chiral fermions in the theory. And finally, if we demand n equals to 1 supersymmetry in addition to all of this in the 4-dimensional standard model, then this places a restriction on the holonomy of the manifold. And in 6 real dimensions or 3 complex dimensions, the holonomy turns out to be SU3. Now, of course, it wasn't clear whether such manifolds should exist, but interestingly, a classification of manifolds due to Berger, probably it was 1965, by their holonomy, produced a list of allowed holonomies for orientable manifolds. And following this, the famous Calabi conjecture proved by Yau stated that an n-dimensional complex scalar manifold with vanishing first-gen class does admit a metric with SUN holonomy. So this led to the class of Calabi-Yau manifolds, and hopefully I've motivated why Calabi-Yau is important in string theory, therefore. So some generalities about Calabi-Yau manifolds are in order. So it can be defined as a complex scalar manifold with a vanishing first-gen class, or equivalently with holonomy group SUN, or possessing a globally defined and nowhere vanishing holomorphic N form. So for Calabi-Yau three-folds, it would be the 3 form. A bit of a notation here: J is the complex structure and G is the metric. We'll move this here, perhaps. Okay. Right. Now let's talk a bit about the moduli space of Calabi-Yau three-folds. There are very interesting results in this regard, which are decades old now. So the total parameter space of a Calabi-Yau manifold consists of parameters related to its structure as a complex manifold, as well as parameters related to its deformations of its Kähler metric. So these two spaces have different dimensions, which are captured by Hodge numbers, H11 and H21, which are the only two unspecified Hodge numbers for a Calabi-Yau threefold. And this leads to the classic Hodge diamond that we might see in the next slide. But before that, this is an opportunity to briefly state mirror symmetry, that if you swap the, sort of loosely speaking, if you swap the Kähler structure moduli space and the complex structure moduli space, you get a mirror pair. So this is a very loose statement of mirror symmetry. So this is the Hodge diamond that I was referring to. So the only non-trivial topological properties, only non-trivial Hodge numbers, unspecified Hodge numbers that a Calabi-Yau threefold has are H11 and H21. Otherwise, the structure is shown on the left. And this changes for Calabi-Yau fourfolds. For example, now there's a class of Calabi-Yau fourfolds which have more non-trivial topological properties. And of course, there are many possible Calabi-Yau geometries, and they feature in different ways in different forms of string theory. But also there are these other manifolds with G2 holonomy, for example, that lots of people work on. I will mainly be talking about CCs here. So that's one of the classes. But there are also these hypersurfaces in reflexive polytopes for which I have produced a plot here, or borrowed a plot rather. So the x-axis here denotes the Euler characteristic, and the y-axis is the quote-unquote height, which is the sum of the two Hodge numbers. The Euler characteristic is actually twice the difference of the Hodge numbers. So there's a lot of interesting structure here. These are around 500 million geometries. So there's plenty, but they all seem to fit into this fantastic form. The tip of the Hodge plot is actually quite interesting as well, and they are mainly populated by CCs or CC quotients, etc. And recently we sort of decided to accumulate all possible Calabi-Yau manifolds with small Hodge numbers to see what interesting geometries lie there. In fact, the smallest one is has Hodge numbers 1, 1, and is due to Volcker-Braun, which is an interesting construction in itself. Right. Now, moving forward with some more general remarks about Calabi-Yau manifolds. So the metric is Hermitian. So, and since it is Kähler, it can be, the metric itself can be derived from a Kähler potential. So as the derivatives of some Kähler potential. The metrics, the metric can then be used to construct the Kähler form J, which is closed, and the corresponding Richie tensor is given by this neat formula uh, as the second derivative of the log of the determinant. Now, the reason I'm introducing Richie here is because we are interested in Richie flat metrics, so we'll actually need to utilize this. Now, a Calabi-Yau admits a metric with vanishing Richie curvature, and this metric is unique in its scalar class. However, till date, no analytic expression has been found for a Richie flat metric of a Calabi-Yau threefold. So in fact, for K3 surfaces, I was referring to recent results by Shamit Khachru and others, where it has been, there has been a lot of development. However, it has escaped Calabi-Yau threefolds, which kind of motivates all these several numerical and machine learning approaches taken over the years in this direction. Now, the manifolds that we will focus on in this talk are numerous. So we'll talk about the quartic K3, the Fermat quintic, and another member of the Dwark family of quintics. And we'll also talk about a couple of other non-trivial CCs, which are phenomenologically very interesting. So they are the Tianya manifold, which is listed as follows. And it is phenomenal. Before I explain the notation of CC, I would like to point out that the Tianya manifold is phenomenologically very important because it actually has a freely acting Z3 symmetry, and upon quotienting and building a string model on the quotient, it actually yields phenomenologically interesting semi-realistic string standard models. Right. Now, I must explain what this notation means, unless it is clear to everyone. If it is, then I apologize. What's happening here is there are two projective spaces, which we consider as the ambient space, in which the Tianya manifold is embedded. And the embedding is given in the form of three polynomial equations, which are written alongside. The first couple of equations are cubic and have variables in the respective P3s. And the final equation, which really ties the variables together, is linear in variables of both these spaces. So this is what the Tianya manifold is. This, without specifying the alpha, betas, and gammas here, which are the coefficients of the polynomials, you can't find a specific member of the family. So these alpha, beta, gammas are essentially, one can think of them as complex structure moduli. Speaking of topological properties of the Tianya manifolds, the Hodge numbers are 14 and 23. And the Euler characteristic is therefore twice the difference between them and equal to -18. Now, another manifold to mention in the same breath as Tianya is the Schwann manifold, which incidentally is the transpose of the configuration matrix for the Tianya, but it is topologically completely different. The Hodge numbers are 19 and 19, and the Euler characteristic is 0. And in fact, I took this opportunity to introduce an equivalent representation of the Schwann manifold in terms of this for those who constantly play with the CC dataset might not actually find this listed in the CC. This was constructed otherwise. but it leads to an equivalent, it leads to the Schoen manifold. And the reason I'm introducing this here is because later on, when I talk about certain other things, such as discrete symmetries, this becomes important because discrete symmetries, as it turns out, is a function of the representation of a CC. So certain symmetries, which can be linearly realized in the expanded version of the CC configuration matrix, will actually be non-linearly realized, or worse, impossible to find in the compressed version of the CC configuration matrix. So what are the mathematically motivated methodologies for Calabi-Yau metrics? So the two big ones are obviously Donaldson's algorithm, where the metric is iteratively calculated using a certain procedure. And the second is a Richie Flow. Now, I will talk about neither, but in our paper, we touch upon both. So if I have opportunity at the end, I will mention a few comments about them. Well, just without going into too many details about Donaldson's algorithm, essentially you start with a valid Kähler potential on a projective space in which the Calabi-Yau is embedded. And this is the form the potential takes. And one might question why this form. It's actually a very a valid Kähler potential on this, and it becomes clear why this is valid if I explain what the quantities are. So S alpha is an element of a basis for degree K holomorphic polynomials over the manifold. And if the dimension of that basis is nk, then you can define this other matrix, capital H, or tensor rather, in this fashion, wherein you see an iterative procedure involving computing this integral gives you a stable balanced metric, which is what H is. And due to Donaldson's theorem, this is guaranteed to exist. So as you increase K in some limit, the metric obtained from the balanced metric approaches the Richie flat metric for the Calabi-Yau. So let's say one has been able to follow this procedure, as many people have. How do you measure how good your outcome is? How close to Richie flat your obtained metric actually is? So to this end, a measure was introduced where the measure itself is given by this integral. And essentially, it exploits the fact that the volume can be computed using either the holomorphic and anti-holomorphic top forms or the Kähler form. And so these two ways of computing volumes gives you a measure of flatness. And it's not clear until this point why this is a measure for Richie flatness, but it will be clear now because one might consider creating a second kind of measure given by this norm of R, and it can be shown, please don't ask me, but it can be shown that this is equivalent to the sigma measure written above. So essentially, a more precise statement would be that as the sigma measure approaches 0, the R measure goes to 0 as well. Are there any questions until this point?
Yeah, I had a question. This is Bernd Sturmfels. Can you just say a word of how these objects are represented in the computer? Are we talking about symbolic computations, numerical computations? How do you actually communicate potentials and metrics to your computer?
Right. Thank you for the question. Well, so as far as the work I am presenting right now is concerned, these are, there is an analytic starting point namely the Fubini-Study metric. And after that, there's a matter of computing the Fubini-Study metric on a bunch of points that need to be randomly sampled from the geometry. And beyond that, it is very numerical. Does that make sense? So actually, maybe perhaps my next slide might answer your question. So yeah. So essentially, even before you get to the business of finding metrics, you need some points on which you'd like to evaluate your metric or train or test your metric, and those points need to be generated in a careful, uniform fashion.
No, I understand, but so at every point in the manifold, you have a matrix or tensor. You numerically evaluate something like a symmetric matrix or a is that correct?
Yes, absolutely. Absolutely. Yeah. Yeah. Thanks for the question. So I'll come to numerical details now. Essentially, before we even try to get to the numerical metrics, I would like to emphasize that this is not a traditional machine learning exercise, because in a traditional machine learning exercise, you have data. Here we have no data. Here, actually, what we are trying to do is to solve a very difficult PDE. And the way machine learning is being used in this work is to say that, okay, machine learning provides a fantastic optimization scheme, namely backpropagation. And it can also provide highly expressive ansatz for a function, namely a deep neural network. So when you combine the two, you can use it to solve partial differential equations. And this goes back to, I think, late 90s in the machine learning literature when this was proposed. And it's being picked up in different communities to solve different PDE and ODE systems. So that's basically the machine learning methodology that we have utilized here. Right. However, although we do not require any data as such, we, for the purposes of evaluating our results and to actually come to a representation, a neural network representation of our metric, we need to sample points uniformly from the manifolds that we are looking at. So there are two cases here. One is the simple case of CC hypersurfaces, and we are going to talk about pharmaquintic, another member of the dwarf family, also the quartic K3 surface, as well as the simple complex torus. So essentially what is being done is these manifolds are embedded by the equation by some degree n+1 equation. And the ambient space here is a complex probability space of degree n dimension. So if we want to sample points uniformly on the manifold, then we start by choosing points randomly on some hypersphere, and then join up those points to form lines and find out the intersection of those lines with the manifold. And those are the points that you then obtain, which you can think of as being uniformly sampled from the geometry. There are further details about this, but perhaps I should move on to state that for CCs that are not hypersurfaces, you need a slight tweaking. So since we also work towards a Richie flat metric for the Tianya manifold, we had to adapt our sampling strategy a little bit, and we described this in the paper. Essentially, we are trying to sample points uniformly. We start by sampling points uniformly on some hypersphere, as well as planes and lines formed out of those points. and then we find out their intersection with the geometry, and those points we then take to be uniformly distributed on the geometry. And like I said, there are further details, and I'm happy to take questions on that later, or one is referred to the paper itself. Right. Now, since we have a machine learning strategy, so we need a couple of things. We need an architecture, and we need a loss function. So the loss function that we are working with here has three main components. Actually, only three components exactly, not main. So one is the sigma measure, which captures the Richie flatness that we discussed before. The second is something that measures Kählericity. So since the metric is derivable from a potential, it needs to satisfy this condition on the right, which I'm pointing with the mouse, which then can be formalized into a measure, kappa. And finally, the metric also has to agree on different patches in a meaningful way. And that is captured by this measure called mu. I'm sorry, I haven't explained what this capital M is, but it essentially is the difference between the metric on a patch and the transformed version of the metric from another patch. So it involves Jacobians, and it helps further specify the parameters of the neural network that mimics the Richie flat metric. So essentially, now the plan is that we use this kind of a modular architecture, modular because we found it very useful to separate out the eigenvalues of the metric from the rest of the stuff. And it allows us to easily play around with what version of the loss function we intend to use. If someone's only interested in determinants or just the eigenvalues of the metric, then we can simply switch off this part of our architecture. So essentially, it takes some number of inputs which come from the ambient space, and it goes through two neural networks which output relevant quantities. And implicitly, what we are using is some sort of decomposition of a positive definite entity, namely the metric, and the LDL decomposition. So you get the diagonal part from this neural network, and you get some lower triangular matrix from this, and you can use them to construct the metric, reconstruct the metric. Right. Now, right. So before I get into results, does anyone have a quick question? Okay. If not, I'll carry on. So, right. Maybe I should spend another, I should make a couple of more comments here. So essentially, these neural networks that together, that combine to give you the metric, have a lot of parameters. Now, I assume most of us are aware of how a neural network looks. It has a lot of unspecified parameters. And the hope is that if you are performing your machine learning optimization part correctly, then those parameters will tend to slowly converge towards the closest approximation of a Richie flat metric that it can mimic. So therefore, the whole business is to play with a large number of parameters here and use an optimization algorithm to specify them using the loss function that I mentioned before. Right. So let's look at some results. Okay, I still have around 8 minutes or so. Okay, so so the quartic for the quartic K3 surface, this is a summary of the results, but I should explain what is going on here. So Actually, I'm not sure if the thing is visible very well, but let me explain. So in the first column of plots, actually, let's focus on the first row. In the first row, the first entry gives you the sigma measure for training and test points. So we compute the sigma measure for both these sets of points, and we see over the course of training, denoted by the x-axis called epochs, we see improvement in the sigma measure. In fact, it is going very close to 0. And remember, I said there are 2 ways of computing the volumes. So if you compared them, plotted one against the other, then you see, if you're doing things really well, then you would see agreement along the line y equals to x. So initially, at the time the network was initialized, the distribution, the plot essentially looked like a bunch of points randomly distributed. However, they have all fallen in line after training, indicating that actually for the points that we have supplied to the network, it is producing volumes that are more or less correct. The other 2 rows, the 3 rows actually represent slight differences in the architecture. So in the first one, if I remember correctly, yes, it's to do with some activation function called ReLU that we use. And in the second set of plots, we use a tan hyperbolic activation function. And finally, we use a sigmoid function. Right. And one point to note here is that if we go back to the architecture here, activation function plays an important role here. Because if you are modeling your metric by some neural network, which ultimately outputs a piecewise linear function, for example, if you use ReLU, then you're confined to that class. However, there are other classes of functions being generated by use of other functions. So that's why we decided to work with all of them and compare them. Nonetheless, these are the plots for the quintic. Again, the sigma measures for all 3 kinds of architecture on the training set are falling fast. On the test points, it's doing more or less okay. Not so much with the sigmoid activation function. That's something to note for future analysis. The volumes agree on the training set to a very impressive extent. And right, so we also tried further experiments with the quintic where we took a large number of points. We took 500,000 points, and we see fantastic trends for the sigma measure. In fact, we can see here the sigma measure is around 0.025 or something around that number. Nonetheless, and if we monitor the 3 different parts of the loss during the training process, we see that they are all decreasing. And now I would like to point out, and this might resonate with many people, that this class of multi-objective optimization problems is notoriously difficult. So there is a lot of machine learning engineering that one has to do to get all the 3 losses or all the n losses they might have in their problem to even have the right trend. So here is a plot from our paper showing that this indeed does happen for our architecture. Now, one interesting point about our architecture that I would like to point out is that although we have played around with the activation functions, our overall framework is actually the same for all the various manifolds we consider across dimensions. For the complex torus, for the K3 surface, the quartic K3 surface, the Fermat quintic, and so on. Here is some result on the complex torus, which we actually showed in the paper. This is sort of a non-neural network approach. It involves using as an ansatz not a neural network, but a dressed up version of the Fubini-Studi metric and solving an optimization problem. And it turns out, actually, in this particular case, the optimization problem is solved very accurately. And the predicted flat metric that we find for the complex torus is actually just a rescaled version of the true metric. Now, I didn't get to speak about Richie Flow, and I suspect I will not have time, but we did talk about Richie Flow in our paper, and we used a standard Mathematica PD solver to actually conduct Richie Flow on the real torus. And lo and behold, the figure on the right, the y-axis is the scalar curvature, and the x-axis is the angular coordinate. And initially, the curvature takes the form of a periodic function. However, with time in the flow, the curve converges to something that is flat. Now, also I wanted to show you results about the Tianya manifold. So again, going back to the previous approach of using neural networks, we do see fantastic outcome both in terms of sigma measure as well as these volume distributions. Finally, actually, I probably need to wrap up quickly. So without saying anything further about discrete symmetries at this point, I would just like to point out that although we were not planning on learning discrete symmetries, it turns out that once we inspected the network, it was learning certain toric symmetries across on various manifolds. So in fact, this one is a plot for a K3 surface. And one of the architectures ends up learning discrete symmetries over the course of the training. And the same thing happens for the quintic. You see the green curve is one of the architectures which ends up learning discrete symmetries. Now, just take a couple of sentences to wrap up. What is the future directions that we need to take are as follows. Before addressing the physical bits, I would like to state that there is a lot of data that now we have been able to accumulate, namely the network's parameters over the course of training, and we would like to derive hints from them as to what the underlying function might be. And in this regard, topological data analysis and the formalism of neural tangent kernel, as well as spectral analysis of weight matrices will shed light. And just to make a point, the spectral analysis gives you eigenvalues for weight matrices in some network. And it turns out in this example, the whole spectra actually lowers over the course of training. The red one is simply keeping track of the highest eigenvalues. Anyway, these are the broad future directions, towards electron mass, every string theorist dream. We'd like to generalize to other CCs, and with the recent hints about discrete symmetries, we'd like to work towards an AI-driven symmetry classifier. Thank you for inviting me to speak, and we have had lots of discussions with various people who I would like to thank.
Okay, well, thank you very much, Challenger. Shall we just thank the speaker quickly? So I think we'll take just one question, because I appreciate we should move on, and maybe during the break later on, Challenger could answer any more questions. So Sven, you've got your hand up.
Yes, thanks, Challenger, for this very nice talk on your work. It's clearly a very interesting topic, and so the question is as follows. So the networks that you find, how do they compare the results to, say, taking Sam Donaldson, taking Hettering-Mercer, in terms of the accuracies that you're getting? Mm-hmm. And subsequently, now you seem to suffer a little bit of overfitting in your plots. Can you comment a little bit on why, it seems to be that for us that sampling is not expensive. So why you decided to not always use new points whenever you're training?
I see. Okay, to answer your first question, Sorry, I forgot to add this plot. I should have. So, of course, people who have worked with more closely with Donaldson's algorithm can provide you answers about what the sigma measures should be. But of course, and we use that data, and we also extrapolated that data to figure out at what order do our algorithms end up converging in terms of Donaldson's K metric, and it turns out it's around 16. Yes, there is overfitting generally if it is not taken care of. However, can I quickly ask you what you were specifically referring to about that?
Yeah, so you were showing these kind of figures in terms of the performance of the sigma see in terms of train and test set. And so it looked like that very much your performance on the train set is very much better than on the test set. And so that's kind of the typical sign, right, that we're starting to overfit. And
that's
so
right.
It seems like very, very cheap actually to always use new points. So not just work with a fixed test set, training set.
Agreed, absolutely. So in fact, this is what I would show you. So in fact, as it turns out that we ended up noticing that if you use a large number of points, this overfitting issue goes away. So for the Fermat quintake, in one of the experiments, we used 500,000 points, and you see there is no overfitting. It's actually generalizing very well. So both the test and the train sigma measures are dropping over the course of training, and the volume distributions are completely aligned along the line y equals to x. So you're right. If you use, even in your approach, you might have noticed that the same thing is happening. Wherein if you use fewer number of points, the neural network itself has a large number of parameters. So it's gonna there's a potential for overfitting. However, we saw that with increasing the number of training points, that goes away.
Fantastic. So we'll have to save further discussion for the break. So let's just quickly thank Challenger one more time.